Okay, I'm Sathasivam, a PMR fellow from ICTVM. So this is week 4. So let's start with today's topic. So the today's topic is we will deal little bit about normal subgroups and the isomorphism theorems. And if possible, we'll discuss about some quotient groups also. Okay. So let's start with this one. Okay. So the first problem says you have this group Z2 cross Z2 and you are quotienting with the normal subgroup. Okay. So since it is a abelian group, so what is this particular group? This group is nothing but 0, 0 and 1, 0. Okay. So you are quotienting out with this group. The question is, okay, what is this group? What is it isomorphic to? Okay. So the main idea of the today's one is to actually try to see how to use the first isomorphism theorem, or I mean all of the isomorphism theorem, in particularly the first isomorphism theorem. Okay. So what we are claiming here, this is a kind of equal to uh, Z2. Okay. So that is the claim. Now let's see how to prove it. Okay. So let's do it here. So we look at the Z2 cross Z2. So we want to say it is isomorphic to Z2. Okay, so that was the claim. So this particular quotient is isomorphic to Z2. Okay, so basically isomorphism means you have to give a map, right? Now from here I'm giving a map to Z2. Okay, so how I am giving? Uh, so if you look here, there are 4 elements here, right? So you have 0, 0. Okay, and I'm mapping this to 0. We have 1, 0. So I'm mapping this also to 0. We have 0, 1. And I'm mapping this element to 1. And we have 1, 1. This also I map to 1. Okay. Now you can verify this is actually a homomorphism. Okay. Okay. So you have to take 2 elements and then you have to add them together and you have to see that it goes here. Okay. So, but for example, you take these 2 elements. If you add it, what you will get? If you add these 2 elements, you will get 1, 0, right? And then 1, 0 has to go, will go to 0. Okay. Now if you map here and then you add it, you will get 1 plus 1, but 1 plus 1 is also 0. So you can see it is matches. Okay. But you have to check all of this is a homomorphism. So I probably skip that step that this is a homomorphism because it's not hard to check, but you just have to do main combination. So you have 4 here. So you have to do all the 16 combinations. So it's a trivial exercise, so you can verify it. Okay. So later I will probably tell you if you have something, some group like this, how do you construct a homomorphism? So it's actually enough to only give define the homomorphism on these 2 elements. Okay. Once you define these 2, then the other will come as a consequence. What I will tell you later how to do like this. But now this is the homomorphism. Let's look at the kernel. So what the first isomorphism theorem says is so if you have a homomorphism from G to H, what the first isomorphism says is G by kernel of phi is isomorphic to image of phi, right? So here you can observe that the image of phi is basically Z2. Okay, so you have all the 0 and 1. So image of phi is basically Z2. Okay, so in our case, we have a phi from Z2 cross Z2 to Z2. Okay, so this is the phi that we defined earlier. So if you look at the image of phi, this is nothing but Z2. Okay. Now what we have to compute is we have to compute the kernel. So let's look at what is the kernel. Kernel is the set of all elements that goes to 0, right? So only these two elements goes to 0. So the kernel is basically these two elements. So kernel phi is nothing but 0, 0 and 1, 0. Okay. Now you apply first isomorphism theorem. So what you get is your group, which is Z2 cross Z2, divided by the kernel, which is the subgroup. Basically, this is the subgroup, not. So we have the subgroup, and this is isomorphic to the image, which is Z2. So if you want to see visualize it, this is kind of like a projection. If you know linear algebra or something, this map is kind of like the projection map. But anyway, basically what you're doing is you take a comma b and you are just mapping it to b. That is what you're doing. So if you look at the map here, the way you defined, what happens is you just take the second coordinate. That is what you're doing. Just ignore the first coordinate and take the second coordinate. Okay. So okay, probably I told you to verify this is a homomorphism, right? But let me verify it also directly here. So if you do like element wise, then you have to do for every element, but you can do it directly. So basically what the map is here, what is the map, you take ab and you're mapping it to b. That is exactly what you're doing here. So let's verify it is a homomorphism. Let's take two element phi of ab plus cd. Okay, let's add it and then take phi and then we do the other way around also. This is phi of a plus b c plus d. Okay. Now, if you apply phi, what you get is c plus d. Okay. Only look at the other way around. Phi of a plus b. This is b. Phi of c plus d. This is sorry. Okay, made error here. So you have to add the coordinate wise. Okay. So this is a plus c plus b plus d. Okay. So if you add this a plus b plus phi of c plus d, this is nothing but b plus d. Okay. So basically you are just adding these two elements, which is b plus d. So you can verify these two are the same. And this phi is a homomorphism. Okay. So we have done the first question. Let's move on to the second one. So the first question we did exactly just apply the first isomorphism theorem, we get that. So let's do the second one. So here we have a symmetry group on 3 letters, and we have a subgroup generated by the 3 cycle 1, 2, 3. Okay. And we want to see what is this group is. So you have S3 mod subgroup generated by 1 to 3. Okay. So what we are claiming is this is actually isomorphic to Z2. Okay. So let's try to prove it. Let's first find out what is this subgroup is. So this subgroup contains all the elements. So it's a cyclic subgroup, right? So it contains, if you have a cyclic subgroup generated by A, this contains all the element of the form A power I, right? Or A power N if you want to call it. So let's try to compute what are those. So if you take 1, 2, 3, and if you just square it, so this is basically 1, 2, 3 times 1, 2, 3. So let's try to compute it. What is this? So in this one, okay, I have to go like this. 1 goes to 2, and then in this one, 2 goes to 3, right? So basically, where the 1 goes to 3. Okay. Now, next one, let's look at where the 3 goes. 3 goes to 1 here, and 1 goes to 2 here. So 3 goes to 1 and 1 goes to 2. So here 3 goes to 2. Let's look at the 2. 2 goes to 3 and the 3 goes back to 1. Okay, so 2 goes to 1. So I can close the bracket. Okay, let's do 1, 2, 3 cube. This is nothing but 1, 2, 3. 1, 2, 3. Okay, so this is nothing but 1, 3, 2. 1, 2, 3. Okay. So this 2 we have just computed, it is equal to 1, 3, 2. So let's compute this. So here you look, 1 goes to 2. So 1 goes to 2. And 2 goes to 1 again. Right? So basically, if you look, 1 goes to basically 1. Okay, let's look at the 2. 2 goes to 3 here. And 3 goes to 2 again back. Okay, so 2 also goes to itself. If you look at the 3, 3 going to 1 here. And 1 goes to 3 here. So 3 basically go to itself. So this is nothing but identity. So what we are computing right now is we are just trying to compute what is this subgroup generated by 1, 2, 3. And so basically we are taking the squares and cubes and everything. So we have seen that if you take 1, 2, 3 power 3, this is identity. Okay. So what are the elements we have? I probably will call it as E. So the subgroup generated by 1, 2, 3, this is nothing but identity 1, 2, 3 and 1, 3, 2. Okay. So, and you can see this is a cyclic group, right? This is a cyclic group, and you can see it is isomorphic to Z3. Okay, because this power 3 is identity. So, this is Z3. Okay, so this we have. Now, what we are actually interested is to find the quotient of this. Right? So, let's try to find the quotient. So first of all, how do you know this is a normal subgroup? So in order to find the quotient, we first have to know the subgroup is normal, right? So let's try to prove a general statement, and from which we just directly conclude this is a normal subgroup. Okay. So let's prove a lemma, or maybe I will call it a theorem also. Suppose G is a group, and H is a subgroup of G, with the index is 2. Okay. So basically the H by Z has a order 2. Then H is normal. Okay. So this is one of the statement. If you have index 2 subgroup, then this is always normal. Okay. Well, we can prove it, but for now, let's assume this statement, and we'll finish the problem. Then we can come back and try to prove this one. Okay. Okay. So let's assume this statement. So here, if you observe, this group has order 3, right? So this group has order 3. Look at what is S6, sorry, S3. So you look at the index here, S3 divided by this particular group. Okay. So this index is nothing but the size of S3 divided by the size of this group. But that is 6 by 3, which is 2. Okay. So the index is 2 here. So this hypothesis is satisfied. From that, we can directly conclude that this subgroup is a normal subgroup. Okay. So this is very useful statement. It's a very trivial one, but it's very helpful also. Okay. So what we have is so this subgroup is a normal subgroup. So we usually write like this is the symbol. We say it is a normal subgroup. Subgroup we usually write like this. Normal subgroup you use this symbol. So it's a normal subgroup of S3. Now what we are going to do is we have to say this is isomorphic to what? That is a question, right? And the claim is we are going to claim that this is isomorphic to Z2. Okay. And if you want to claim, you have to first give a map and you have to prove that this is the isomorph. Okay. Okay. Let's try to prove it. So the map is basically you take the phi from S3 to Z2. Just wondering whether I have to give a map or there may be a better way to do it. See, one can give a map and do it, but there may be a better way, you can do it. Okay, anyway, I will just give a map directly. So this identity, or I probably call it E, this I maps to 0. Okay. So S3 has 6 elements, right? We just give the map. So the 1, 2, 3, we maps to 0. Because you see, we want this to be in the kernel. So we may map all these kernel elements to 0. Okay. So 1, 3, 2, we will maps to 0 here. So there are other 3 elements, which is 1, 2, this we map to 1. And 1, 3, we map to 1. And 2, 3 also, we map to 1. Okay. So now you can check that this map is actually a homomorphism. Check phi is homomorphism. Okay. Okay, so once you checked this map is a homomorphism, now if you look at the kernel of this, you can see the kernel is basically these 3 elements, right? So now you apply the first isomorphism theorem. So we have the image is isomorphic to Z2 and kernel of a phi. This is isomorphic to this subgroup. Sorry, 1, 2, 3. So subgroup generated by 1, 2, 3. It has 3 elements, of course. So now let's apply the first isomorphism theorem. Okay. By first isomorphism, what you have is S3 by this subgroup. So this is isomorphic to Z2. Okay, so we have done this. Okay, here if you look, one has to actually has to check that this is a homomorphism. It takes some step, but you can actually see it. So what you can observe is the following. You observe this one. So if you take 1, 2, this is actually, let me call the subgroup as K. The subgroup generated by 1 to 3, let me call it as a K. So if you look at 1 to K, you can prove that this is equal to 1, 3K and this is equal to 2, 3K. Okay. And once you have that, you can probably directly give map module with this also. So that will also be fine. But you observe this and then you can try to see that this is a homomorphism. You just need to compute it, but so I just leave it as exercise. But one thing here you can observe is, see, doing this kind of thing is a little bit ugly. So you have, there is so many maps. So you are mapping all the elements. Now you have to check its homomorphism. So you have to do step by step. Like you have to take all the elements, all the combination of element, and you have to compute this, right? You have to compute phi of A plus B is phi of A, phi of B, right? And you have to do for all elements, and that is actually not always easy. So here you have 6 elements, so already you have a 36 combination. If your group is too big, then doing in this way is not a really good idea. So later we will give a way where we can, instead of doing all these things, we can directly say how we can do it. Okay. So in that sense, if you go to this group also, so here we are giving like this, right? We are mapping every element. In that sense, if you really wants to compute, this kind of map is not a good way of giving it. But if you're giving a map like this is a good way. So this both means the same thing. Whatever you do here, you are doing the same thing here. But one thing you can observe is if the group is bigger, this kind of computation, although a computer can do it, but for a human, this kind of maps are not a good idea. But this is a good idea. Okay, because we can easily compute it here. Okay, so if you do in general, you can do it, but otherwise it's not easy. So later, right now I'll just leave you to compute, but later I'll just remark that it is possible to there is something called generator and relations. Okay, so for example, if you have so this just a remark. If you don't understand, don't worry about it. We will come back to that. If there's a time, we will come back to that. Otherwise, you can study by yourself. Okay. So, for example, if you take the cyclic group Z10, so what you can have is the cyclic group is basically isomorphic to, it is kind of A power, sorry, generated by A. Uh, so this is generated by a symbol A with the property that A power n is equal to 1, right? So this element is called the generator, and this is called the relation. Okay. So what you can say is any group can be written as a generator and a relation. So that was one of the theorem. When you do something called free groups, you will study all these things. And once you have a generator and relation, which every group has, so once you have it, what you can do is it's enough to, if you want to give a homomorphism, it's enough to give on the generator, and you just have to prove the relations are satisfied. So anyway, that is for example, here I will just give an example here, little example. So if you want to give a map from, let's say, Z4 to Z2, it is enough to give a map from the generator, which is the one is the generator here, to anything. Let's say map it to 1 here. And what is the relation here? Relation here is x power 4 is equal to 1, right? So this is the relation in Z4. Or basically the relation is basically 4 is equal to 1, sorry, 4 equal to 0. This is the relation, and I just have to see that relation is satisfied. So if you look at phi of 4, which is nothing but phi of 1 plus 1 plus 1, you write it as phi of 1 4 times, and this is equal to 4 inside this group, right? And if the relations are satisfied, uh, so if you look here, 4 is actually equal to 0 in Z mod 2Z, in Z2. Okay, so 4 is basically 2, right? In Z2, 4 is 0. So this relation is satisfied. Here 4 is 0 is the relation here. The same relation is satisfied here also. So this map became a homomorphism. Okay. So whatever I am writing here, okay, so basically you can leave it here. So this phi map, once you define on the generator, how do you define on any other element? You define on any other element is right like that, because any other element here can be written as 1 plus 1 plus 1 plus 1, right? So if you want to define on 4, what you do is you take the phi separately. Okay, so that this is how it is defined. And this map will be homomorphism provided if the relations are satisfied. So there is a better way to give a homomorphism, but right now let's just do like this, and probably you can modify a little bit for now. It will help you to see how to compute also, but later we can do in a better way. But anyway, let's leave it and let's move on to next problem. Okay, So here we will do little bit interesting, which we will not usually do in the first course. But this is interesting, so let's do it. So what we are going to say is we are going to show that GG, okay, which is it is called as a commutator subgroup. Okay, so this is basically the subgroup generated by elements of the form. Okay, so it's a GH, G inverse, H inverse. Okay, so the claim is this is a normal subgroup. So let's see how to prove it. So let's take a element like this. So let's say if your G is generated by, let's say, A1, A2, etc., AN, and suppose you want to prove that G is a normal subgroup. Okay, so it is enough to prove that G, sorry, let's say where H is generated by this, and which is a subgroup of G. And if you want to say H is a normal subgroup of G, suppose. Okay, so if you want to say that, it is enough to actually prove that it is enough to show G A I G inverse belongs to H. Okay. So this is basically enough. You don't have to prove for every element. It's enough to prove only on the generators. Okay. So this is a standard thing, but probably I will assume this also. You can try to prove this. So there may be little some exercise. If you want, you let me know. I will prove it now itself. Otherwise, we can try it as exercise. So assuming this, let's try to prove this statement. Okay, so we are going to say that if you take some other element and conjugate it, this element will again it's again a commutator. That is what you want to prove. So let's take this element GH G inverse H inverse, and you take some element. Let's say X belongs to G. Okay, and this element belongs to the commutator GG. So let's look at the conjugation. So we want to prove that conjugation also belongs to the same group, right? So X, GH, G inverse, H inverse, X inverse. Okay. So if you look at this element, so what we can do is everywhere inside you multiply X inverse. Okay. So what you're going to do is X, G, X inverse, H, X inverse. Mm, okay. X inverse, and then I have to G inverse. Again, you do X inverse, and then you take the H inverse, X inverse. Okay. Okay. So what you basically do is you take this and everywhere inside you put X inverse. Okay. So this is what we are doing. Now what you do is you group this thing together. Okay. So now if you see what happens is the following. Okay, just give me a minute. Okay. Probably you should not directly write like this. Let me take. So what you have is you take x and take a g. Maybe I'll write x in different symbol, g in different color. So you take g. You put it as x inverse x here. Okay. And you have a h here. And again write x inverse x. Okay. And you have again g inverse. Put x inverse x. H inverse. And then you have x inverse. So now combine these things. Okay. And you can see this is nothing but you see it as let's say some element. So let's say you call this as some alpha, you call this as some beta, and you can observe this whole term is nothing but alpha beta, alpha inverse beta inverse. Okay. So this alpha, this beta. What is the inverse of this? So the inverse of this, you just have to apply the. For example, you take alpha. Okay, not alpha. So x inverse you take, and you compute the inverse of this. You need to apply the Saxo lemma. So it goes in the other way around. So it gives x inverse inverse, g inverse, x inverse. This is nothing but x, g inverse, x inverse. So you can observe this is the term here. Okay. So if this is alpha, this is nothing but alpha inverse. If this is beta, this is beta inverse. Okay. So you will get the same element again. So you get alpha inverse, beta inverse. So this element again belongs to commutator GG. Okay. So we just proved. So that means this commutator is a normal subgroup. Okay. But anyway, you have to prove this statement. Once you prove this statement, you can verify this. Okay. The reason why we are working with this commutator subgroup is the following. So what we can do is once you have the commutator subgroup, which is a normal subgroup, if you quotient it out, you will get a abelian group. Okay. So I was thinking I should do this exercise, but I'm not sure if you actually understand what is happening here. If you are struggling with this, probably it's not a good idea to go further. So probably I will come back to this later. Or you tell me if you are interested, we can do it. Otherwise, we will come back to this later. But anyway, at least you know the fact. So this is a abelian group. If you quotient it to the commutator, this will be abelian group. And the interesting property of this abelian group is the following. Okay. So this is called the universal mapping property of abelianization. So this particular group, this is called the abelianization of G. Okay. So in particular, if you take a group, the group need not to be abelian, right? So what we are going to do is we are going to divide that group by some other normal subgroup to make that group abelian, and that is called the abelianization. Okay. So this has a nice property which I will state here. So this is called universal mapping property of abelianization. So it says the following: suppose if G be any group and A be an abelian group, okay, and if you have a homomorphism phi from G to A, which is a homomorphism, then it factors through this abelianization. Okay, I will let you know what I mean by factors through, the phi factors through. So you have a map from G here, and there is a map going to A. So this is your phi. Okay. So there is always a natural projection from G to G5, right? So from G to abelianization, there is always a natural projection. So what is this map? You take G and you map to G. Okay. So this map you always have. So what happens is if you have a homomorphism from G to A, and if this A is abelian, then what happens is this map factors through this. So basically there is a 5 bar here such that this diagram commutes. So if you go via from G to A, it's same as you go here and then go here. So there exists 5 bar such that going like this is same as you go via the natural projection and go here. Okay, and this 5 bar is also unique. So probably I will write it properly. So there exists uh, unique 5 bar. Okay. Such that let me call this as pi. Such that what you have is pi composed with 5 bar. This is 5. Okay. So what is the use of this? The use of is the following. If you want, if there's a homomorphism from G to A, you can just see it as a homomorphism from abelianization to A. Okay. So that is the advantage of doing this. Okay, in order to do that, what you have to prove is this is the abelian group you have to prove, and then you have to go here. But probably I will skip it here. See, I have written that problem, but one thing I didn't notice is the statement that I have here, right? I didn't notice it here. So this is kind of somehow uses the generator and relation. So basically, I'm telling this is the generator of H. So later, everywhere when you go there, we might need the generator and lesson. So which I didn't recall before. I didn't notice before. I thought it's all easy. So I went because in some courses it was defined earlier, but I just remember that in our courses it's not done. So that's why I'm skipping this problem. But at least you will have an idea what is actually happening here. So this is why we study the abelianization, and the interesting property is any homomorphism will actually factor through some quotient. Okay, let's come back to some more interesting problem. So the first one, what we did is we try to identify what is the quotient group, right? So the very first question, if you look, what we did is we kind of identify the quotient group. So we said, what is this? This is nothing but this is isomorphic to Z2. And this is also isomorphic to Z2. So we kind of identify it. Now let's compute all the homomorphisms. So the question is find all the homomorphisms from S3 to Z6. Find all homomorphisms from S3 to Z3, and there is another group here. Okay. So here you observe, I can actually use this, right? So if you look here, these are all abelian groups, right? So I can actually use this idea. So what you have to do is you have to find the commutator, a commutator of S3, and then you can quotient it out and you can do it. Okay. So that is one way, but there is other way. I will say using the first fundamental theorem, the first isomorphism theorem. Okay. So one way I will just hint it is you find the commutator S3 S3. This is not easy to find, okay, but you can prove that this is basically equal to this subgroup that which we have seen. Okay, and then if you quotient it out with S3 by the commutator, you can observe that this is basically isomorphic to Z2. Okay, so if you want to find a homomorphism from here to S3 to Z6, it's same as finding the homomorphism from Z2 to Z6. Okay, so this we have done already. This is the first question we have done, but this one has to compute. So this same as finding the homomorphism from Z2 to Z6, and there is only two homomorphism are there. Okay, so that is one of the way you go via the abelianization and you do it. But since we couldn't able to finish this problems properly because we need a little bit more theory to do that, which I haven't realized. So that is my fault. So I will give another idea. So here there are multiple ways to do find all the homomorphism. So I will give one which uses the first fundamental theorem. So first isomorphism theorem. Okay. So what you can observe is the following. So first isomorphism theorem says you the following, right? So this is kind of the general idea. and depending on the problem you need to change it. So it's not explicitly you can use it, but at least this idea more or less sometimes works. And of course I have to say not always it works, because you need to know a little bit about the group to use this idea. The idea is the same anyway, but you need to know about the group. So the first isomorphism theorem says the following: G by kernel is isomorphic to the image phi. Okay. So what you know, this kernel phi, it is a normal subgroup. Okay. So this you keep in mind. Okay. So now what we are going to do is we are going to find all the normal subgroup of S3. Okay. So what our idea is, what we are going to do is we find all, so normal subgroup of G. Okay. Suppose if you want to find, let me write here, to find all homomorphisms phi from let's say G to H. Okay. What we are going to find is we first find all the normal subgroup of G. So what next we are going to do is we going to take G by N. Okay. So and so next one is find G by N. Okay. And the third one is check whether G by N is a subgroup of H. Okay. If G by N is a subgroup of H, then there is a homomorphism. Okay. Then, but again, you have to see how many homomorphisms are there. So there is a little more. You have to do a little more after this. But once you have this, at least we know there is a homomorphism. To find all the homomorphism, you have to find all the homomorphism between Gn to Gn. You have to do some automorphism computation. Uh, I will do it via example. So let's compute this first one. So the first one says we have to find all the homomorphism from S3 to Z6, right? So let's look at the normal subgroups of S3. So we have one. This is the normal subgroup. Okay, and S3 is a normal subgroup. So we have also proved this 1, 2, 3. This is a normal subgroup. Okay. So these three groups are normal subgroups we know. Okay. So we also have some other groups, like let's say the subgroup generated by 1, 2. So which is nothing but 0 and 1, 2. Okay. So there are three more subgroups are there. 1, 3. And you can see that subgroup generated by 2, 3. Okay. So you can write it. So there are basically 6 the subgroups are there. Okay. Now the question is which of the things are normal. So what we have proved is these three are normal. The question is whether these three things are normal. Okay. So let's prove that these groups are not normal. Okay. So claim 1, 2 is not a normal subgroup. Okay. So I will just do for 1, 2, and rest of the 2 I will leave it as exercise. It goes exactly the same way. So what you do is, see, if you want to say something is normal, what you want to prove? Normal means x and x inverse. This is contained in N for all x in G, right? This is the claim you want to prove, to say something is normal. And I am claiming here something is not normal. That means I have to produce a x here. So I have to say there exists a x such that this is not possible. Okay. So what we have to show? We have to do, so there exists x in G such that this is not correct. That's not contained in N. So let's try to find some x. Let's just try to do all the combination and see which one is correct. So one can see, let's say 1 3 I took, 1 2 I do, and then 1 3 inverse. Okay, you can observe that 1 3 inverse is actually 1 3, because if you do it twice, you will get identity. So this is nothing but 1 3 1 2 1 3. Okay, now let's compute it here. So let's start with 1. 1 goes to 3 here. So 3 does not go anywhere here, right? So 3 goes to 3 here, and you see 3 goes to 1 here again. Okay, so 1 goes to 1 again. Okay, so let's say what is 2. So 2 here, 2 is fixed here. When the 2 is not written here, that means 2 is fixed. Okay, so 2 goes to 1 here, and here you see 1 goes to 3. Okay, so 2 goes to 1 and 1 goes to 3. So 2 goes to 3. Okay. Now let's look at where the 3 goes. Here 3 goes to 1 and 1 goes to 2, and the 2 was fixed by this permutation. So 3 goes to 1, 1 goes to 2, and here 2 is fixed. So basically 3 goes to 2. Okay. So what we have seen is, if you look at this conjugation, you will get 2 3. Okay, but observe that through 2 3 does not belongs to the subgroup. Okay, thus the subgroup 1 2, identity 1 2, this is not normal. Okay, similarly you prove for these two. Just take you take 1 3 and do with some other thing, you will get it. So these three things are not normal subgroups, and these three things are normal subgroups. Okay, so let's we find out all the normal subgroup. Let's what can we do again? So let's look what are the possibility for kernel is basically these three subgroups, right? So let's start from here, 5 from S3 to Z6. Okay, so the possibility for kernel is three subgroups. Let's say what is the first possibility? Let's say kernel is equal to identity. Okay, in this case what happens? G by kernel, which is 1, sorry, S3 by kernel. So this is basically S3, and this will be isomorphic to the image, right? Image of Z6, sorry, image of a 5. Okay. So what is the image of 5? See, this S3 has order 6, right? So the image of 5 also has to have order 6. It's a isomorphism. In particular, isomorphism means it's a bijection. So what we have is size of S3 is 6. And because of the bijection, we get the image of a 5. It also has the order 6. And we see this image of 5 is also a subgroup of Z6. Okay. But the both has the same order. So what we conclude? We conclude that image of 5 is basically Z6. Because it's a subgroup, but they have the same order. So it has to be the same. Okay. So basically what we have is this, the image of 5 is nothing but Z6 itself. Okay, so what we have is S3 is isomorphic to Z6. Is it possible? So this is a contradiction. Why? So if you look here, S3 is a non-abelian group, right? All the elements will not commute, but Z6 is a non-abelian group. Under isomorphism, the notion of abelianization, cyclic, these are all preserved, right? So if you have a phi, which is a isomorphism from G to H, so this is isomorphism. Then if this guy is abelian, H will also be abelian. If G is cyclic, H is cyclic. The same holds for other way around also. If H is abelian, then G is abelian. If H is cyclic, then G is cyclic. So these two things are either abelian or cyclic together. So here you observe this is not abelian, and you can see that this is abelian. So that is not possible, and hence the kernel cannot be one. Okay. So the contradiction occurs because we assume there is a homomorphism with the kernel is one. Okay. And such a homomorphism is not possible. Okay. So first this kernel we avoided. Okay. Now let's look at the other easy case. Kernel. So this is the second one. Kernel is actually S3. Okay. So in this case, what the map you have? This map is basically S3 to Z6. You map any x belongs to here, map it to 0. Okay. So that is the map, which and this map has a kernel S3. Okay. So this is the unique map you have, because the kernel is S3 means every element goes to 0. So this is the only possible map. And you see, this homomorphism always exists. Whatever the group G and H you put, this homomorphism always exists. Okay, let's look at the third possibility, which is kernel of phi is nothing but 1, 2, 3. Okay. So in this case, if you look at phi, so this is a what? This is by S3 by 1 to 3. We have to get a map in from this to Z6, right? This is by first fundamental theorem. Sorry, first isomorphism theorem. And you observe that this is actually isomorphic to Z2. Okay. So the question is Z2 sitting inside Z6? If Z2 is sitting inside Z6, then I can give a morphism. Otherwise, I cannot give a morphism, right? So what we are doing is we are kind of go in a reverse direction of the first isomorphism theorem. The first isomorphism theorem says if this is a homomorphism, then the image is contained here. Of course, image is contained here, and the first isomorphism theorem says that is then this Z2 is isomorphic to the image. So that is the first isomorphism theorem says. What we are doing is assume if there is a homomorphism, then this has to be contained here, right? So let's see if there is a subgroup contained here. If there is a subgroup contained here, then we will give the homomorphism. So that is what we are doing. Okay, so let's look at Z6. Inside Z6, is it cyclic? Is Z2 contained in Z6? So when I say Z2 contained in Z6, I mean up to isomorphism. Okay, I'm not saying exactly seeing it as two elements. I'm saying up to isomorphism whether it's contained here. And the answer is true. Answer is yes. So you can look at this particular group 0, 3. Okay, you can see this is isomorphic to Z2. Take 3 two times. Okay, so basically 3 plus 3. This is so 3 plus 3, which is 6. This is 0 mod 6. Okay. So this subgroup is actually isomorphic to 2. If you take this twice, and that became 0. Okay. So we have a subgroup. So let's give a map. So now we have to give a map also. You remember this. So what you have to do? 5 from S3 mod 1, 2, 3. Okay. We need to give a map to Z6. Okay. So if you observe here, this group is generated by this element 1, 2, 1, 2, 3. Okay. In fact, you can suppose let me call this 1, 2, 3 as K. Let's call. Okay. So then what you can observe is this 1 to K. This generates So why is the case? See, first of all, observe that 1 2 does not belongs to K. So 1 to K, it is a non-trivial element in this group, right? And you can see this group is actually isomorphic to Z2. So it's a cyclic group. And if you have a Z2, any non-trivial elements generate a Z2, right? It's a cyclic group. I mean, it's a cyclic group such that there's only two elements, right? One element is zero, another element is any non-trivial element. So this element also generates. So similarly, one can argue that 1 3 also generates that, and you can check. This is actually, these are all same. 1 3K, 1 2K, and 2 3K. These are all same coset. Okay. So basically, it is generated by any of this. Up to just a representative is different. Okay. So what we are going to do? So how the map we are going to define? We go from S3 to K to Z6. How we are going to do? We do this 1 to K. We map it into uh, so we map it into 3. Okay. Because you observe here, 0 3 is the subgroup. Okay. And 0K, we map it into 0. Okay, so this is the homomorphism from S3 by K to Z6. But we actually want homomorphism from S3 to Z6. We don't want homomorphism from here. So then how do you, so let me call it 5 bar. Then how do you get a homomorphism from S3? So simply you compose S3 here. Okay. So this is the 5 bar. And that's a natural projection here. So phi is basically nothing but the pi compose 5 bar. Okay. So this is the homomorphism from S3 to Z6. Okay. So how many homomorphism we got? We got one homomorphism here, and for this kernel we got one homomorphism, and this kernel we got one homomorphism. So basically, totally we got two homomorphism. Okay. Thus, there are two homomorphism. Okay. So what is the first homomorphism? So I will write it explicitly for you guys to see, but because we are doing first time, I'll write it explicitly. You take any x maps to 0. So this is the first homomorphism. Okay. So what is the second homomorphism? It is also goes from S3 to Z6. So the identity goes to 0. Any element of K, which is this subgroup generated by 1 to 3, this goes to 0. Okay. And 1 3, this goes to 3. 1 2, this goes to 3. 2 3, this goes to 3. Okay, so these are the two homomorphism, and in fact these are the only two homomorphism. So why these are the only two homomorphism? Because here you see, I want the image to be, if you go here, this one if you look, this one if you look, what you get is this is isomorphic to Z2, right? And I want the image has to be Z2. Inside there is only one possible image. So inside Z6, there is a unique subgroup of Z2. Order 2, there is only a unique subgroup. The uniqueness follows from the fundamental theorem of cyclic group. Sorry, give me a minute. So the uniqueness follows from the fundamental theorem of cyclic groups, right? So the fundamental theorem of cyclic group says, it says the following: if you have a Z10, if you are working with the Z10, for any D divides N, there exists a unique cyclic group of order D. Okay, so this is the first fundamental theorem. Sorry, this is the fundamental theorem of cyclic group says If you in Z10, it kind of classifies all the subgroups. It says if the order divides n, there is a unique cyclic group of order D. So basically, there exists a subgroup of order D, and that subgroup is unique as well as it's cyclic. Okay. So what about if D does not divide n? If does not divide n, there is no subgroup, right? That is what Lagrange theorem says. Lagrange theorem says if we have a subgroup, then the order of the subgroup divides the order of the group. Okay. So if D does not divide n, then there is no subgroup of that order. Okay. So this is we are using this actually here. So there's only one subgroup inside Z6 which is isomorphic to Z2, and that is basically this particular group here. Okay. Yeah, and here also one can say there is a, see, this is one such a map. This is a generator I'm mapping to 3, right? One can also argue, see, the subgroup is I can map a generator to 0 also. Okay, if you map generator to 0, then what happens is this map became 0 map, right? So when you compose it, you will get a 0 map, and the kernel will not be equal to this subgroup. The kernel became S3. If you want a kernel to be equal to this particular 1 to 3, so then the only possibility is you map this to 3. Okay. So let's look at the next problem. So next problem is you take S3 and you go to Z3. Okay. So once you keep, sorry, I need to go later. So once you keep practicing, you will able to solve it. This is maybe the first time you're doing it, may be a little bit tricky, but it will be easy. Okay, so the second question is find all homomorphism from S3 to Z3, right? Again, we know all the normal subgroup. Normal subgroups are basically the identity. So this is basically identity, S3 itself, and the subgroup generated by 1, 2, 3, which has order 3. Okay. So if you want, you can write this is isomorphic to Z3. Okay. So now we have to compute again. Do the same thing. First is the kernel of phi is identity. If kernel of phi is identity, what do you get? We get S3 is isomorphic to the image, right? Image phi. Okay. And image phi has to be contained inside Z3. Okay. And you can see in particular that says that the S3, because there is no kernel here, it says that S3 is contained in Z3, right? Which is not possible. This implies S3 is contained in Z3. Okay. Contained means up to isomorphism, it is contained in Z3. Not directly, I'm not telling directly, but via isomorphism, it is contained in Z3. But that is not possible. Why? Because you see, order of S3 is 6, but order of Z3 is 3. And telling that S3 is contained in Z3 is not possible, right? A 6 element set is contained in a 3 element set, which is not correct. So this is a contradiction. Okay, so this is not possible. So there you get no homomorphism from identity. So let's look at the other two. Okay. So let's look at the kernel is so here we are considering the case the kernel itself is S3. So that map means if you go G by kernel, okay, so this is identity. And what is the map? This is isomorphic to the image of a phi, right? So there is only one map here you can give. Again, this is same as S3 to Z3. The map is given by any x you take goes to 0 here. Okay, so that is the map. Because kernel is 5 means every element goes to 0 basically. That is what it says, and this is the only map here. Okay. So now the third part, this is the interesting part. The kernel is basically the subgroup generated by 1 to 3. Okay. So let's look at the GB kernel. So GB kernel is basically G is a S3 by this subgroup 1 to 3. And you can observe that this is isomorphic to Z2, right? So by first fundamental theorem, first isomorphism theorem, so what we have, G by kernel is isomorphic to image of 5, and this is contained in Z3. So what is G by kernel? G by kernel is basically Z2. So what it says is Z2 is contained in Z3. Well, this is not possible, right? Because this is a cyclic group of order 3. This is a cyclic group of order 2. Again, this is a contradiction to the fundamental theorem of cyclic groups. Or you can see contradiction to Lagrange theorem. Right? So the order property does not hold. So if you look here, with this kernel, there is no isomorphism. Sorry, there is no homomorphism. Okay. So the only homomorphism you get is this one. So this is the only homomorphism you got. Okay, right. So let's move on to another one. So the third problem is S3 to Z2 cross Z2. So this was a little bit more interesting, and you can see from here, you can see that you still have to do a little bit of more work. Okay. So this is kind of little more complicated than Z6, but it is not like very hard anyway. So let's try to do it. Again, the kernel has only 3 possibilities. So the kernel phi has only 3 possibilities. Okay, so one is identity, another is S3, another is the subgroup generated by 1 to 3. Okay, so you check this is not possible because this is a abelian group. Sorry, this is a abelian group. This is abelian group. This is non-abelian group. Okay, E is not possible. Not possible kernel as S3 is non-abelian, and this is abelian. So you can also go via the size argument also. The size are different. So the first problem we did via the abelian property. Here we did via the the size property. In the second problem we did via the size property. So here you can use any of this. Okay. So this you avoid. This is not possible. This is possible, and of course there's only one map, right? So second one is kernel of phi is equal to S3, and the map is given by. So map is basically a trivial map. Take x goes to 0, 0, 0. So far there is no problem. The third one is the little bit hard part. So here the kernel of phi is this subgroup. Okay, 1, 2, 3. Okay, and you observe that S3 by this kernel phi or S3 by 1 to 3, the subgroup generated by the cycle 1 to 3, this is isomorphic to Z2. Okay. So basically what we are doing here, we have to say this is a contained in Z2 cross Z2, right? Okay, so how many ways this is contained in Z2 cross Z2? So if you observe here, this image here, this can be contained in Z2 cross Z2 in three ways. How? If you look here, there is a three subgroup of three subgroups of Z2 cross Z2, which is isomorphic to Z2. So what are the subgroups? So look at this one, 0, 0, 1, 0. Okay, this is one subgroup. Another one is 0, 0, 0, 1. This is another subgroup. And the third one is 0, 0, 1, 1. Okay, so there are three subgroups now. So these three subgroups gives you three homomorphism. Okay. So since I think he came back, I will just recall once more, little bit I will fastly recall. See, we want to find the number of homomorphisms from S3 to this group, right? So the possible kernel is only these three. And we have seen this is not possible. The same argument you do. Okay. So S3 is abelian and this group is not abelian. So E is not a possible kernel. Okay. S3 is a possible kernel and the map is just given by a trivial map. Take every element to 0. In this case, 0 is 0, 0. So let's look at what is the, assume this is the kernel and see what will happen. So if you see this is a kernel, then S3 with this is isomorphic to Z2. And now you see whether this I can put inside Z2 cross Z2. But here you can see there are three possible subgroups which are isomorphic to Z2. Okay. So these three possible subgroups give you three homomorphisms. Okay. So how you go there? Let's say you define phi 1 bar, which goes from S3 by K to Z2 cross Z2. Okay. And this maps, 1 to K. This maps to 0, 1. Okay. And you have phi 2 bar, which goes from again Z3 by K to Z2 cross Z2. And this maps 1 to K to 1, 0. Okay. There is another homomorphism, phi 3 bar. Z3 by K. Okay. And this maps to 1, 1. Okay. And you compose this with phi like we do in the first problem. So for example, you define phi 1, which is nothing but phi compose phi 1 bar. So if you want to see it pictorially, you can see here there's a S3, there's a phi here. We go to the image, we go mod K, and then there's a phi 1 bar here, and this is a Z2 present. Okay. So similarly, you do for this two also. Okay. So how many maps you get? You get three maps from here and one map from here. Sorry, one map when the kernel is when there's a trivial map, and you get three maps from here. So there are four homomorphisms. Okay. Now let me do one more thing. See here, your group is kind of like Z2, Z2 cross Z2, something like this. So let me ask this question. Okay. Find, let's say, all homomorphism from let's say Z3 to Z3 cross Z3. See here also there is a same problem, right? Here also we did a similar kind of problem. So if you observe here, this is basically isomorphic to Z2. So what we did is we find a homomorphism from Z2 to Z2 cross Z2. This is what we did. Now we are doing a little bit differently. For instead of 2, we take 3 here. Okay. So now how do you do that? So this question you have to work it a little bit more. So what do you have to do? There is see, the kernel is again the only possible kernel is identity and identity and Z3. These are the only possible kernel. Okay, because these are the only possible subgroups. Okay. And you know, if Z3 is if kernel is Z3, there is a trivial map. So let's consider the case where this gives a trivial map. So let's work with kernel's identity. So basically, we are looking at the injective map from Z3 to Z3 cross Z3. Okay. And you see any homomorphism from a cyclic group. So now I will give you a little bit more info. So if you look at a homomorphism from a cyclic group to any other group, what you just have to do is it is enough to map the one. Okay, as long as it is determined by where you map the one. Okay, so let's say where the one is mapped. That is the question. Now one can be mapped to any element here as long as the order of that element. So one can be mapped to any A here. Okay, as long as the order of A is basically equal to 3, or order of A divides 3. So if you go, probably maybe I'll do in a general statement. Okay, maybe let's finish this and probably I'll remark the general one. Okay, as long as the order is 3, we can give the map here. Okay, so what that means is that you want to find how many element of order 3 is here. The reason I was doing here, okay, probably we go in the same way like we did here, and I will say what is actually the difference. So if you look at the subgroups here, the number of subgroups which are here, there are again only there are 3 subgroups. One is generated by 0 1, okay, sorry, 0 2, 0 0, similarly 1 0, 2 0, 3 0. Okay, and there may be another subgroup here. Well, there will be more subgroups. Yeah, that is correct. So 1 1, 2 2. So this is 0 again. 0 0. But if you look here, these are the elements, 3 elements. But you see here there are 9 elements here, right? There is a 3 possibility here and 3 possibility here. And you take any of these 9 elements, that will generate a subgroup. So how many elements we get from here? 1 2 3 4 5 6 7 elements we got, right? There is a 2 more element is missing, so I will write those 2 elements, which is, let's say, 1 2 you take, and 1 2 if you take and do it again, you will get a 2 1 and 0 0. Okay, so these are the 4 subgroups here. Okay, so if you ask me, okay, how many homomorphism I can get, it is not 4 homomorphism. Okay, like the way we did last time. What we did here, if you observe here, so I take this generator and then I map it to 1 0. Here I map to 0 1, 1 1 I mapped, right? So these are the groups and I map to the generator here. But if you look here, there are more generators. This is a generator of this group. If you look at this group, this is isomorphic to Z3. And you see, this is the generator, this is also a generator. Okay, so I can map to this also, I can map to this also. In that sense, each of these subgroups gives me 2 homomorphism. Okay, so that is what I was trying to say. This one I can map to here. Okay, I can map to here inside this subgroup. Okay, and here also I can map to this, I can map to this, and similarly inside this subgroups. Okay, so anywhere I map this one, I will get a homomorphism. Those homomorphisms are different, right? Mapping one to this and mapping one to this one is a different homomorphism because the one maps differently. Okay. So what I'm trying to say is uh, so the first step what we did is we find this G by kernel which is you know isomorphic to some subgroup, and then what we did is whether this subgroup is contained in our image. So this is the image, right? So if you want to homomorphism from G to H phi, then first what we did is we find G by N and we see whether it is contained in H. Okay, and once it contained in H, there can be a many homomorphism from this to that image, right? So what you have to do again is you have to find all the homomorphism from G by N to G by N. Okay. So there are different possible images. First of all, in this problem we have seen that G by N can be sitting inside this H in a three different way. There are many ways this G by N can sit inside H, and you can also observe that after it you choose a image, there are many homomorphism from G by N to that image. That is what you are seeing here. Okay, so in this case G by N is basically, see this kernel is basically E identity. So G by N is basically this subgroup, and you can see this subgroup can be sitting inside Z3 cross Z3 in four different ways. Okay, but if you look at the homomorphism can be, it can be sitting inside, let's say in this subgroup. So G by kernel, this one is isomorphic to this, but then there are so many ways we can define isomorphism. The isomorphism can come from we map this one to this element, or it also comes from mapping this one to this element. Okay, so let's finish the algorithm that we have here that we started with. So check whether G by N is sitting inside H. Okay, and once you find G by N is sitting inside H, if G by N is equal to some, let's say H1, okay, then find all homomorphism from G by N to H1. Okay, so which is same as telling find all homomorphism from G by N to G by N. Okay, so up to isomorphism these are all same. So once you see that this is okay, when I say equal via isomorphism. Okay, oh, what I mean by equal via isomorphism, see, you see it here. So yeah, this is what I mean by equal via isomorphism. You take this group which is kind of Z2, and this is equal to 0 3 via the isomorphism. It's not actually equal. If you look here, this is some coset, this is something else. These are not equal, but uh, using the isomorphism I'm seeing it as a subgroup of this. Okay, but in this case, if you, the last problem, let me go. I'm sorry for moving between the pages, but I just want to tell you, I just want to finish the algorithm. That's why I'm trying to go, but I'm sorry for moving in between the pages. Okay, it may be hard for you to see, but I'm sorry about this. So if you look here, this Z3, it is contained in here, but there are many ways you can define isomorphism. Okay, so I see it as see, this Z3 is not equal to this group, but via isomorphism I am seeing it as a subgroup. After you see it as a subgroup, there is many ways you can give homomorphism from here to here, and you have to take care of, I mean, many ways you can give automorphism from here to here, and you need to take care of all those things. Okay, okay, now the question is how many homomorphism you can get from Z3 to this. Let's see, there is a trivial map, and again this Z3 can be sitting inside Z3 cross Z3 in one of this following, as one of the following four subgroup. In each case, the map can be given by you take this one to one of these elements, right? If this Z3 is sitting inside this one like this, then the possible maps could be this or this. In both these maps makes this Z3, coming inside this subgroup. Okay. Similarly, you can see for other four. So there are 8 homomorphism you can get from here. So there's a 2, 2, 2, 2. That's a 8 homomorphism here, and there is a trivial element here. Okay. So basically, there are 9 homomorphism. Morphism. So how you do? You map one to some element of one map to A belongs to Z2 cross Z2. So if you observe here, what we actually did is this one can be mapped into any of these elements here. Okay, 0 also we mapped here. The trivial homomorphism we mapped it into 0. Okay, so now from this observation, let me kind of say if you have a homomorphism, if you want to find a homomorphism, but your domain is, let's say, abelian group. Let's see how you can find the homomorphism. Sir, if the domain is a cyclic group, then in general I will we see how we can do the, I mean, how you find the homomorphism. If it is a non-abelian group, you cannot go like this. You have to use the first isomorphism theorem. But if you have a cyclic group, then you can do a little bit better. Okay. I think Sir might have done it, but I will just recall it. So suppose we have a map phi from Z3 or Z10, let me say Z10, to any group G. Okay. Then phi is determined by phi of 1. So what does it means? It means the following. If you want to find any other element x, if you want to find phi of x, what you do is you take phi and then you write 1 x times. Okay. And since it is a homomorphism, what you get is phi of 1. You get this is a phi of 1 x times. Okay. So basically, if you want to find any x, it's same as you take phi of 1 and then add the phi of 1 x times. So this is phi of 1 power x. Okay. So if your group G is as the multiplicative notation, then it is a phi of 1 power x. Maybe I will put n here rather than x. F n times. Okay. If it is if G is additive group, then you have to write n times phi of 1. But it's kind of understood from the context what I mean. So as long as you know where the 1 maps, you know every other element. Okay. So the question is, what are the possibilities that 1 can map? See, 1 can map to any element of G, but there is only one problem here. If you look at the phi of, sorry, this is, let me call this as some m. Yeah. Okay. So, I mean, this n and this need not to be the same. For any other element, you can always take it to the power of. So, your homomorphism is just, as long as you know phi of 1, you know where every other element is goes. Basically, you take to the raised to the power. Okay. So that's where I used the x, but when I changed to the n, that both became the same. That does not have to be. But the problem here is, this 1 is actually equal to n. 1 is equal to m in Z mod nz, right? So we have this relation. So this is what I call as a relation. So we have this relation, and your homomorphism will satisfy this relation. So if you look at phi of 1, and this is has to be equal to phi of m. Okay. So what is phi of m? This is phi of 1 power m. So, but this is 0, and here this I want it to be a 1. I mean, I'm writing like G is a multiplicative group with identity 1, and here I'm just seeing it as a additive group, not phi of 1. Sorry, not 1 is not equal to 0. 1 is not 0 is equal to m. Phi of 0. This has to be 1. Okay. So because this is 1, Since this is 1, you have to have this element also has to be 1. So this is the conclusion. If you have a homomorphism, then phi of 1 power m is equal to 1. Okay. So this is what we have. Suppose if you have homomorphism, okay, then this relation has to be satisfied. Now what we can do is, suppose if there is a element A, let A belongs to G, such that A power m is equal to 1. Okay, then you can always give a homomorphism. Then the map phi from Zm to G, mapping, you map this 1 to A. This is a homomorphism. Okay, so thus if you want to find a number of homomorphism from the cyclic group to G, thus if you want to find number of homomorphism from Zm to G, so what we have to do is we have to find the number of elements in G which satisfy the following. Number of elements in G, number of elements, let me call it as A in G with A power m is equal to identity. Okay, so if you look at, let's go back and see here with this example. If you look here, how many elements here with, see here, what is the relation? It is 3, right? So what we need is we have to find number of elements here, A in this group, such that A power 3 is identity. Or in this case, the additive group, so 3A is 0. Okay. So how many elements here satisfy the problem? So property, you can check. You take any elements here, all these 9 elements. Okay, these 8 elements plus this 0. You take any of this 9 element, you can observe that take to the power 3, add it 3 times, you will get 0. Okay. So there are 9 elements. There are 9 elements, and you can see all these 9 elements satisfy the property. If you add it 3 times, they are 0. So you can map this 1 to any of this 9 element, and that will give you a homomorphism. Okay, but this you can only do for cyclic groups. Okay, if you want to find a number of homomorphism from a cyclic group to any group, just find the number of element of G. Satisfy the property that A power m is equal to 1 if you have that m here. Okay, so I'll just say a little bit more and then we move on to next problem. So here, if you observe here, when we do this computation, you can see this cyclic group is kind of generated by this element 1, right? This is generated by the 1, and you see this is this is the relation here. Okay, so what we are doing here is basically you are mapping a generator. You are mapping this generator of this group to any other thing, but we want to make sure that the relation is satisfied. If the relation is satisfied, that gives you homomorphism. Okay, so this here we are doing for a cyclic group. This you can do in general for any group. Okay, uh, but it's not going to be this easy. Every group has some generator. Every group has some relation, and if you map the generator to any element, as long as the relation satisfied, you can do it. Okay. But in general, this kind of a strategy is true. That go when you study something called free group, and so you can find those things in this particular modules. I'm not sure if you are going to do that in our course. I want to remark it just in case if you're interested, you can you kind of study it. So you look for free groups, generator, and relation. So these are the keywords that you can use to find generators, relation. Okay. So use this keywords, you will get the theorems. Okay. So basically, what you do is you take the free group and then divide by the free group on the generators, and then you have to divide by relation. There's something you have to do it. It's a kind of big topic. I mean, it takes some time, so I'm not going inside. But if you're interested, you look for this one. The same thing what we did here, the generator mod the relation, that you can do in general. Okay, so let's move on to different question here. So far what we did is we try to compute some explicit examples of homomorphisms and sorry, explicit examples of quotient groups, and we try to compute some homomorphisms. Uh, but there are you can do much hard problems. So for example, you can find okay, what is the all the homomorphism from Z2 cross Z2 to the same thing, Z2 cross Z2. Okay, or you can compute something like S3 to some dihedral group, 2 times 3. Let me call 2 times 3. Okay, so these problems are more harder, but we will come back to that. I'm not sure if you have learned the dihedral group, etc. uh, so probably maybe next class we can introduce dihedral group and we do more problems related to this. But more or less the idea is the same. You find the kernel and see G by N is contained in you have a homomorphism from G to H. Find the kernel, find the normal subgroups here, look for G by N, see whether it is contained inside H. If it is contained in the H, there is a homomorphism, and but there can be many homomorphisms, you have to adjust that. Okay, that's all. There can be many homomorphisms, because if G by N is let's say sitting inside H, uh, there can be many subgroups for which this is isomorphic, as well as if it is isomorphic to one subgroup, let's say H1, it is equal to H1, then there are many ways you can see the homomorphisms. Sorry, there are many ways these two are equal. Many homomorphism gives these two are equal, so that you have to take care of it. Okay, so let's move on to a different problem. I think sir has did a little bit close to it. We'll just do it again. So let's G be a group and F be a finite field of order Q. So if you don't know what is a finite field, you just see it as let's say ZP. Okay, so this is one of the finite field. There are the other finite fields. Okay, so if you don't know this terminology, you just imagine this is just ZP. So there's a group in which the addition multiplication are defined and there's some property, but just see it as a ZP if you don't understand. Okay, so the first problem says prove that GLNF by SLNF is Q minus 1. Okay, so we will use the first isomorphism theorem to prove that. So what you do is you take the map from GLNF, and there's a map to F star. Okay, what is GLNF? This is basically set of all invertible matrices, right? Invertible matrices mean determinant is non-zero. Okay, so there is a map which is basically determinant map. You take a map it into determinant of A. Okay, and basically what is this SLN? SLN of F. This is nothing but set of all matrices A from GLN of F. This is the definition, with the property that determinant of A is actually equal to 1. Okay. So if you look at this ZP, if you consider this ZP star, which is other than ZP, other than 0, you take all the other elements. Okay, so maybe here you assume that F is basically nothing but a ZP. Okay, so if you look at this one, which is 1 to P minus 1, this is a group under multiplication, right? Last time also we have did this. Okay, we have said that this has an inverse, etc. So this is a group under multiplication. And what is the size of this F star? The size of this F star is other than the Q, we are taking all the other elements. So this the size is basically Q minus 1. Okay, anyway. So these are all the maps such that the determinant of A is 1. Okay. Now what we are going to do, we have to find what is the GLNF by SLNF, right? Let's apply the first isomorphism theorem to this one. Okay. So one thing you can observe is this this is actually a surjective map. Let's first say the determinant is surjective map. Okay. For right now, I'll just assume this f is nothing but the zp. Okay. And we have a map to zp star. Let a belongs to zp star. Okay. Then consider this matrix. Okay. So there, sorry, not n, 1. So the first coordinate you put the a, and rest everything you put 1. Okay, and the rest everything you put 0. If you take the determinant of this, so if you have a upper triangular matrix or lower triangular matrix, determinant is just you have to multiply the diagonal entries. Okay, and if you multiply, you will get 1 time a times 1 1 1 will come, and that is actually equal to a. So what it tells you is this determinant is actually a surjective map. Okay, so that tells you this determinant is surjective. Okay, determinant is surjective tells you image of this determinant uh, is nothing but the entire zp star. Okay, see here I assume that f is a zp star. Okay, it is true for any other finite field also. The same proof will goes away, but I just assume z is zp star because some case if you don't understand what is a finite field, it doesn't matter. It you just assume it's zp for now. Okay. Okay, so the first isomorphism theorem says G by not G, GLN GLNF by the kernel of determinant is isomorphic to the image of determinant, right? So what is the GLN by what is the kernel? Kernel is nothing but GLN. Kernel is SLN. Okay, so GLNF. Why kernel is SLNF? Kernel is a set of all elements such that the determinant is 1, which is basically exactly the definition of SLN. So here you can see. Okay, so GLN by SLN of F. This is isomorphic to the image of the determinant, which is a ZP star. Okay. Now you look at the order on the both side. Okay. So order, if you look here, so this GLN by SLN. This is nothing but the order is defined as the index, right? GLN as GLN of F times SLN of F. Okay. But if you look at the order of ZP, this is nothing but P minus 1. Okay. So that is what we got here. So this is equal to this. And that kind of gives you the proof. Okay. So this basically just means, this index is what it means. Okay. Generally, if you have any field of order q, you just say it is equal to q minus 1, and the same proof, you just write it here. Instead of p minus 1, you will get q minus 1. Okay, so what is the interesting thing about this problem is if you want to find the index of something, you can. So the what you learn from this problem is the following. If you want to find, let's say, GLN index by this, okay, so how do you find this? In general, I'm asking you. Okay, so in general, I'm giving you a group which is a GLN, let's say ZP, and I am giving you another group SLN ZP. Okay, so these are all, if you look, these are all matrices, right? These groups are all matrix group. When I write something like this, the element here is actually coset. So now the question I'm asking is to see how many coset you can get. If you compute here, this is it's not going to be easy. Okay, I don't even want to try. Okay, it is very hard here. But what we want is that we want to find the size of this. which is in general not easy. But what we are doing is we are giving a map to this one. Okay, and this map is a surjective with this as a kernel, and that map exists, which is a determinant map. And once you have that, you can see this size is nothing but, because we have isomorphism, this size is nothing but this size, and this is easy to compute. See here, you can observe how this this homomorphism is useful. In general computing this size, you see, you try to compute it, then you can understand. Okay, so probably I'll just leave this, try to compute um, without using homomorphism. Okay, you don't even have to take as a general P. Let's take as a, Z3. Take it as a Z3 and take it as Z3. Try to compute it. Uh, then probably you can understand how this is useful. Because as long as you don't compute it, what you feel is, we did something, which is something we have done. But the point is the determinant map. You once you try computing, if you feel it is hard, if you feel it is easy, then put, let's say, bigger prime. Okay, so that makes it harder. So then you can observe this determinant map, the use of the determinant map itself. Okay, although see, when you first study the determinant, is just you have matrix, and you do some random operation. That is how we all studied the determinant. But here, from here, you can observe, even though that map is something, there are meaning behind the determinant map. Okay, which usually you will not study in the high school, etc. But if you have some time, we can study something called the multilinear algebra. So I will just remark it here if you're interested. So you might know linear algebra. So, but you try to study multilinear algebra, then you can see this determinant is one of the multilinear maps. Okay, and there is a conceptual way you can define the determinant, rather than what we did in the high school, where the bunch of formula is thrown at you. There is a way you can conceptually see, okay, what is determinant and how it is useful. Of course, there is a geometric way to see it, using that volume of a parallelepiped, etc. But there are, in multilinear algebra, you can see it conceptually. So you, if you're interested, you look through that. Probably. So you can see the power of the use of determinant here. So that is why the reason I put this thing, even though we don't know what is the finite field yet, you just assume it is just a set P. The reason I put is you can observe that usefulness of the homomorphism itself. Okay, let's do some more abstract problems. So this is another question. It says, okay, let me check in the questions that I have. Is there anything that is very interesting? Then probably I'll like to. Okay. Maybe after that problem, I will come back to this one. This one will be more interesting. So the rest you can try. Okay. So this question says the following: prove that if H is the normal subgroup of G of a prime index P. Okay. So what does it says? You have G here, and you have a H here. With this index here, if you look the index here, this is a prime P. Okay. So the index is P. Okay. Then for all K, which is a subgroup of G, so you take any other K here, which is a subgroup of G, what you have is either K is contained H, either this K will be contained here in the H, or this G is equal to KH. Okay. So this is a product of the groups, and this index is actually P. So if you go by K index H, this is P. So this is what it tells you. So I will just say it again. if H is a normal subgroup and K is any random subgroup, so H is a normal subgroup of index P and K is any other subgroup, then either this K is contained in H, so it is contained in H. So when you write the bar, it means containment. Okay, or this G is nothing but HK, as well as this index is P. Okay. Sometimes if you draw like this, you can kind of see what is happening. Okay. In group theory, usually we won't do this much, but if you go to Galois theory, etc., this is a nice idea and a nice way to look at this, and people usually like it. Okay, so let's try to prove it. So whenever you have a statement like either or, what we always do is we assume one of this is wrong and we try to prove other one. Okay. So I think the first few classes we have explained why the logic is, why we can prove like this, but right now we'll just do that. So let's suppose this is false. Suppose K is not a subgroup of H. Okay. We claim two holes. So it is a R statement, right? So that means either this is true or this is true. Okay. If this statement is true, then we are already done. Okay. So that means we can assume this statement is false and we prove this statement is true. That is what we are going to do. Okay. Suppose this is false, let's assume we will prove this is true. So now you observe the following. This H is a normal subgroup, right? So HK is a subgroup. So what is this HK? HK is nothing but HK, H in H, and K in K. Okay. In general, this is not a subgroup. But if one of this is a normal subgroup, then this is a subgroup. If you want, I can give you the closure property. I'm not sure if we have done it in the class, so I'll just give you the closure property. The rest of the property you can try to figure it by yourself. Okay. The identity inverse are all easy, so you can figure it out. Just the closure property I will give. So let's take a HK and H1K1. Okay. And I want to say this I can write as this form. Okay. Since this is a normal subgroup, okay, since look here, H is a normal subgroup, what we have? We have HK, or maybe, yeah, so H1K, not H1K, give me a minute. Yeah, we have KH is nothing but HK, right? So this is the normal condition, one of the property of normal condition. So this element, if you look here, KH1, this belongs to this one. So I can write it as some other element. So KH1 belongs to KH, so which is equal to HK. That means what? That means there exists H2 such that KH equal to H2, KH1 equal to H2K. Okay. It's not necessarily the same H1 comes, but it's the same coset, but there is some other H2. So this is equal to H2, K, K1. So from here, I'm just replacing it here. Okay. And you can see here, this is another element. This is the element of H, this is the element of K. So you can see the closure property holds. And now you have to, kind of see the inverse also. But once you see the inverse, so probably I will do the inverse also, because you know that, right? If you have the closure and the inverse, then it is a subgroup, right? So closure we did. Let's do the inverse also. HK you take the inverse. This is nothing but K inverse H inverse. Okay. So this belongs to K inverse H, but H is normal, so this is equal to H K inverse. So there is a element H comes here such that this is equal to, okay, so there exists, so it may be some H3 K inverse. Okay, and this belongs to HK. Okay, so this element inverse is nothing but this, and this element belongs to HK. So you can see that this is a subgroup. Okay, so this is subgroup we have. What we are going to prove is subgroup is known, but we are going to say this is equal to G, and we are going to prove that this index is P. Okay, so let's do a little bit, change this diagram little bit more. So you have G here, and you have HK here. Okay, what you are going to prove is this G and HK are same. So let's try to prove it. So what we are going to do is we are going to use that third isomorphism theorem. Okay. Remember the third isomorphism theorem? There is some diagram, right? So I will write the third isomorphism theorem. Okay. Maybe I will just write exactly as in the book. Yeah. So here you got it. So right. Uh, so H and K nouns are with, yeah. So this is what we have. Suppose we have a H, comma K, uh, such that so these are all subgroup of G. These are basically normal subgroup of G. Okay. So H is a normal subgroup of G, and K is a normal subgroup of G, with H contained in K, contained in G. Okay. If these are the hypotheses, if this satisfies, then what we can do is we can consider this K by H. So this is normal subgroup in G by H, and we have the following. We have G by H by K by H. Okay, is isomorphic to G by K. Okay, I will tell you what happening here. So if you draw like this diagram, so let's draw it kind of like a diagram. So you have a G here, you have a K here, you have a K here, and you have a H here. Okay, so this G go take the mod K. This one is same as you take a G by H here directly, and then you take H by K here. You can see it kind of cancel out, but up to isomorphism it kind of cancel out. So that was the third isomorphism theorem. Now we are going to use the third isomorphism theorem on this particular chain. Okay, okay, but I want to say that this is P. The entire thing is P. Okay, this I don't know. This length I don't know, but this entire thing is P. Entire index is P. Okay, when I write P on the edge, I mean that index is P. G index H. This is P. That is what I mean. Okay. So let's do it for this particular chain. So we have G here, HK here, and H here. Let's use the third isomorphism theorem. We're going to use this with the order property directly. We are using it. Okay. So what it tells you is you take a GH. So by third isomorphism theorem, so third isomorphism theorem applied it to this particular chain. Okay. What you get is a G by H. Sorry, G by H. Okay, so what it says, G index H is equal to, it's nothing but okay. Maybe I will write from this third isomer, I will write what it is, then probably I will go. Maybe I'll move it a little bit below. First I will write here, then you can, it is clear then. So if you take the order in both sides, what you get is G by H by K by H. This order is nothing but order of G by K, right? Now I want to find this order. This order is nothing but order of G by H by K by H. Okay, this is a G by H, G by K. Okay, so if you want to find order of G by H, you can take it to the other side. So that is what we are going to do. In this case, G by H here, uh, instead of K, we have a HK. Okay, so in this chain, we have G, K, H, but remember in this chain, we have G, H, K, and K. So if you want to find, this is nothing but, so this order is nothing but the index, right? This is nothing but G by HK, and then KH. Okay. So what I know is G by H, this is P I know. This is equal to P I know. Uh, G by H, K by H, no. Just give me a minute. HK by K. Yeah. Okay. So this is what we know. This we know as P, right? So you go here and you can see. H is the normal subgroup of index P. So this index is P we know. Okay. This index we don't know. This index we don't know. But we want to prove that G equal to HK. So basically we want to prove that this is equal to 1. If I say this is equal to 1, because this is a subgroup of G, if we prove the index is 1, that means G is equal to HK. Okay. So that is the claim we want to prove. For that, what I want to say is HK by H. This I want to say it's non-trivial. Okay. Okay. So let's do the HK by H. So what is HK by H? How do you do this problem? You use the second isomorphism theorem. Okay. This is equal to H by H intersection K. No, I think it is K by H intersection K. Yeah, this is K by H intersection K. Okay, so I will go here and I will try to explain here. See, if you go by H K by H, if you go this way, okay, if you want to find this index, is same as finding this index. Okay, if you want to remember the second isomorphism theorem, see it geometrically. If you want to find this index, same as finding this index. If you want to find this index, it's same as finding this index. Okay, you can visualize it kind of like this. So now we want to find this index, so it is same as finding this index. Okay. uh, okay, this I have. Okay. So this tells you this K by H intersection K. So this is nothing but HK by H. Okay. So index of HK by H. Okay, you call this, let's say 1. Sorry, you call this, let's say 1, and you call this one as 2. Okay. Anyway, this is not kind of enough, because here you have observed we haven't used one of the hypotheses that we haven't used this, right? So what we assume is K is not contained in H. That property we haven't used yet. We will first use this property to prove that HK is equal to G. Let's first prove this, and then from there we will get this. Just using the second thing, you will get. Okay. Let's claim. So the claim I want to make uh, is HK is not equal to H. So what we know is H is contained in HK. I know. Okay, but what I'm claiming is it is not equal to H. That means I'm claiming it is strictly contained in is what I'm claiming. Okay, why is that following? Why? Because you see, K is not a subset of H, right? This is not true. Thus, there exists K in K such that this K is not an element of H. Okay, so if you look at this K also belongs to HK. How this K belongs to HK? You see it as 1 times K. Okay, so this belongs to HK, but this K should not belongs to K. This K does not belongs to H. So that means this inequality is strict. Okay, so H is a strict subgroup of HK. So what does it tells you is HK, if you look at HK by H, this is not equal to 1. Okay, let's go above and we use this property. Okay, by 1 I probably copy paste it and then we will do it below. Copy it and paste it. So this is by 1. We have this, but we know this is equal to P, and so what are the possibilities for this two? P is a prime, right? So what are the possibility for this two? It is either 1 or P, and it is also either 1 or P. But what we have seen is this is not equal to 1, so it has to be P. Okay, if this is P, that means this has to be 1, right? If this is also P, then you will get a P square equal to P. That is not correct. Okay, so this tells you G. So this is 1. Okay, so that means G equal to HK. Okay, so we proved the first statement that we want to prove. Use the third isomorphism theorem. We proved the first statement. Let's do the next one. We want to find the K by K intersection H, right? So that let's look at the second one. K by K intersection H is nothing but HK by H, right? So let me copy this also. Paste it. So this is what we want to find, but HK is G. So this is GH. Okay, and GH is given to be P. And that's all, we are done. So this is what we want to find, and here you go and observe. This is P. This is what we want to find, and we completed that. So whenever you do the second isomorphism theorem and third isomorphism theorem, always kind of remember this diagram. So in fact, second isomorphism theorem is called the diamond isomorphism theorem, because if you look here, it's kind of goes this way. You have a H here, so you have H, you have a K, you have a H intersection K. Okay, so the second isomorphism theorem kind of says like this. This subgroup, if you take HK and you quotient it with H, this is same as taking K and quotient it with HK. Okay, so this quotient is same as this quotient, and this quotient is same as this quotient. Okay, so basically it says HK by H is isomorphic to K by H intersection K, or K intersection H, doesn't matter. So if you draw this one, then you can easily see it's just the opposite diagonal. You have to kind of match it, whichever the diagonal comes. So it is also called the diagonal isomorphism theorem. Okay. And diamond actually. It's called diamond because it kind of looks like a diamond. Okay, I had prepared actually quite a few questions, but we will stop here for now. Yes, 2 hours is over, so we'll stop now.